Welcome back, class. So we are starting over a new chapter, which is actually about the diode applications. So far we have learned about the construction of the diodes, and we have learned about the basic operation of the diode in the forward bias and the reverse biased. And we know that for the forward bias operation, we will have the positive high voltage here and the negative or the low voltage here. So we should have high and the low, then the current will flow in this direction and we will have the forward bias operation. If you provide the negative here and the positive here, so basically the diode will act in the reverse bias operation, and there will be no flow of the current. So here the current will flow only in the forward bias direction. So we have learned about this, and we have solve the different examples of this. So now in this chapter we are going to focus on basically the practical applications, that how we can actually use this diode for the various practical applications. And the top application is the AC to DC conversion. For example, you have a cell phone charger. So you are plugging into the power socket, so you get 220 volt AC, and your cell phone is charging at 5 volt DC or 3 volt DC. So you have to convert that 220 volt AC to 5 volt DC. So we can convert this using the diodes, and this process is called rectification. In this chapter we are going to learn about this, that what is this rectification procedure is, that how we can actually use diodes to perform this operation, how we can use diodes to convert the AC to DC. That is the core of this chapter. So the first in the rectification process, there are two kinds of the rectification: half wave and the full wave rectification. First we are going to study about the half wave rectification. So let's first have a look at the general understanding of the rectification. So let's say we have an AC signal from the AC socket, the power socket, and the signal is like the peak value of the signal is 110 volt. So usually we have 120 volt AC signal, but in some countries they use the 110 volt as a standard. So this is just a number. It could be 100, 110 or 120. The peak value of the AC signal. And then the frequency of the signal is 60 Hz. Frequency is this is the time period, one time period of this signal. The one time period of this cycle of this signal, and frequency is the inverse of the time period. 1 over f is the time period. So 60 Hz is the frequency of this. So if we use the half wave rectifier, so half wave rectifier, what will half wave rectifier do? Let's say this is my signal. So this positive half cycle, it will be appear at the output. The negative, it will be gone, positive it will appear, negative will be gone, positive will appear. So if only the positive cycle appeared at the output, this is called half wave rectification. So then there is a full wave rectification. Full wave case is that the both cycles, the positive and negative cycles, are appearing at the output. So like this is the one cycle, this is the second, one cycle, second, 1 second. This is called full wave rectification. So basically our target is, we want to convert AC to DC. AC is changing with time, like this waveform, like this waveform here. So here after rectification, for example for the full wave rectification, we get this signal, only the positive cycle of this waveform. Then we use a filter. So that filter actually filtered out the envelope of this, and we get this envelope here, and then we use a regulator, and then finally after regulation we get a DC voltage here. So these are actually the components of the power supply, the filter and regulator. So our focus of this chapter is the rectification process, how we can actually get this one, and finally we are at the end, we are also going to study the filtration. So this is an example that why we are actually studying this chapter. So this is an example of the cell phone charger circuit. This is the circuit, okay. So this is the AC circuit from the power socket, and usually we have a transformer. So this is 220 volts. So we use a step down transformer that usually converts the 220 volt to 9 volt AC, okay, or 6 volt, 7 volt AC, okay. Then this is a full wave rectification circuit. We are going to study that how it is actually working. Then the next we can actually implement this rectification circuit using this. This is a bridge of 4 diodes. So we use 4 diodes, and by using 4 diodes we can get the rectified output. So this is a diodes which we can use, and then we do the filtering. We have a regulator, and then we can get the output DC. Okay, so this is the inside of a typical charger. If you just open your charger, you can see that. So this is actually a transformer. Okay, and this is the filtration net, the capacitors, and like here is the bridge network and the other components. So for example, here this is the inside circuit of another cell phone charger. Okay, so basically maybe after this chapter, okay, you can build your own charger at your home, cell phone charger. It's not difficult. You just need a transformer, you just need a bridge rectifier, then a capacitor, a regulator, and then you can get the output value. Okay. Now let's have a look at the half wave rectification. What is actually the rectification? How diode is actually perform this? Okay. So we know that in the last chapter there are different kinds of the diodes modeling. Okay. So we are considering, for the understanding first case, let's consider the ideal diode. Okay. So the ideal diode is, what was the ideal diode? So as soon as I have the positive here, it will be short circuit. Okay. And like the forward biased, and if I have negative here, it will be open circuit. Okay. So let's say now what is actually happening, let's say this is an AC signal. Okay, so this is the positive cycle and this is the negative cycle. Okay, between T0 and T1 we have the positive cycle. So when the positive cycle is coming here, okay, so at that time, okay, we are having the positive value here. Okay, this is the positive cycle. Okay, positive value. Okay, and this is the negative. So the negative is coming here, which is connected, like this is the common negative. So the positive value is coming at the anode of the diode, and the negative is at the other end. So this diode, because we know that if the positive value is coming here and negative is here, it will work as the forward bias. Forward bias means it will just act as a short circuit here. So the current will start flowing. Okay, so the current will flow. So basically this positive half cycle is coming at the load end. So if we just calculate the V out at this, which is basically, V out is what? Basically the flowing current multiply the resistance value. Okay, so we will actually get this positive half cycle at the output, the same positive half cycle at the output. Okay, now let's look at the this is the positive half cycle term. Now let's have a look at the negative half cycle of our waveform. So this is the negative half cycle. So when, now what is actually happening here? So this is the negative and this is the positive. Okay, so negative is connected with the anode and positive is connected with the cathode. So when negative is connected with the anode and positive is connected with the cathode, we have the reverse bias. Reverse bias means now here it's open circuit. Open circuit means no current. So there will be no output voltage. Output voltage will be, output voltage is I into Rn, right? So I is 0, output voltage will be 0. Okay, so basically for the first cycle from like T0 to T2, we will get the first positive half cycle. Then the next cycle will come and we'll get the next positive half cycle. Then next positive half cycle. So this is called half wave rectification, because only the half of the input pulse is being rectified, it's converted to the being converted to the output because of the diode operation. Half wave rectification. Okay, let's have a look at this animation. This is the forward bias operation. Positive cycle is coming. Okay, diodes short circuit, we will get the positive. Now it's the reverse bias. Negative cycle is coming, open, and we will get the no output. Okay, so this is just the animation. Positive cycle, the diode will act as forward bias, short circuit, the current will flow and we will get the output. Negative cycle, no current, will get no output. Okay, so this is just the conceptual explanation, and like we just connect the multimeters at the input So at the multiplier, at the input, we will get the complete waveform, right? We are getting the complete waveform, but at the output, we will just get the half wave. Okay, this is called rectified output of the diode. Now we considered the ideal diodes, right? So we considered that as soon as we are having the positive here, this is short circuit and the current will flow. Okay, what if the diode is not ideal? Okay, so if the diode is not ideal, okay, then it will actually, when we are actually positive here, it will act as a forward bias, but now there is a potential drop of 0.7 volt here. Let's say the peak value is Vp, okay, then the output value, we will get this positive cycle at the output, okay, but the amplitude of this output will be this peak value minus the potential drop of the diode. Okay, so for example, let's say this is 10 volt, okay, then the peak value of the output, it will be 10 minus 0.7, 9.3 volt. So if you just make the non-ideal diode, okay, the only difference will be the peak value of the output waveform, okay, because for the positive it will start acting as a forward bias, and finally it will the non-ideal, it will only affect the peak value of the output. Rest of the operation will remain same. Okay, again this is the illustration of the same concept. Okay, like if this is the peak value, okay, now let's say like you have to get the 0.7 volt. Okay, so basically when the 0.7 volt is applied, the value of the let's say this is like 1 volt, then this is like, let's say 0.7 volt. Okay, the value is increasing, and once it reaches the 0.7 volt, at that time your diode will become forward bias, and only we will get this part of the circuit. Okay, this is another explanation of an illustration of the same concept. Okay, then for negative there is no output, and again on the positive cycle. So basically the peak value, it will be this is the 1 volt, the potential drop is 0.7, so Vp minus 0.7. okay, 1 minus 0.7, this peak value will be 0.3 volt. Okay, for the non-ideal configuration. Then there are some important summary parameters for the rectified output waveform. Okay, so let's say if this is the peak value of the waveform, the peak value, like for example 10 volt, then we can actually get an average value of the waveform. So this is actually an AC signal. Okay, and this is the one cycle, one complete cycle. So like the waveform is coming from here and then going here, and then this is the second waveform, this is the one cycle. Okay, so like if you see here, so this was pi, this is 2 pi, so the one cycle time period is 2 pi here. Okay, so we have the peak value of the AC waveform, so we can also get the average value of the AC waveform. Average value of the AC waveform is also called the DC value of the signal. Okay, so if you want to get the DC value of the signal, okay, so it can be actually written as V average. So let's say this is the AC signal, and this is the AC signal expression. Okay, sine of theta. So the average value or the DC value, it will be equal to integration of your signal for the complete time period, for the one complete cycle. Okay, so one complete cycle is 0 to 2 pi, and we will divide this with your time period. Okay, so this is the expression for the calculation of the average value. Okay, then there is another value which is called RMS value. Okay, so we can calculate the RMS value. Okay, so RMS value square basically is equal to, okay, this will be equal to again 1 over time period, and we will integrate for the complete time period. Okay, now we will integrate square of the signal. Okay, so it will be V square into sine square theta into tan theta. So if you are calculating the average value, you will integrate the same, like just let's say this is the V. Okay, so we will just integrate V, and if we are getting the RMS value, we will integrate with the square of the signal. So most of the time when we are actually referring to the the AC signals, we use the RMS value. Okay, so if you simply calculate the RMS value and the average value for this half wave rectified signal, this is Vp over pi. So try this at your home. Just try to integrate. We will discuss this during the live session. So the DC value is actually equal to the peak value divided by pi. Similarly, if you calculate the RMS value, this is equal to the square of the RMS value is VP square over 4, or the RMS value is VP over square root of 2. Okay. So in other words, okay, for example, if this is the peak value, then the average value is VP over pi, and the RMS value, okay, the RMS value, it will be coming something like here, that is equal to VP over square root of 2. Okay. So by from the peak value we can calculate the DC value and the RMS value of the waveform. Okay. This is an example for this, and we will discuss this during the live session. Another important parameter for the rectified circuit is the peak inverse voltage. So in the last chapter we have studied this. The peak inverse voltage is the maximum voltage of the diode at which actually it will behave as works in the reverse bias. Okay. So in this case, for the positive half cycle, our diode is working in the forward bias. For the negative half cycle, okay, for example, if this is the VP value or the 10 volt, then this is the minus VP, right, or minus 10 volt value. Okay. So basically in this diode, okay, so the peak inverse voltage, the maximum value of the inverse voltage at which the reverse biases occur, it will be this value, the negative half cycle maximum value. Okay. So peak inverse voltage here, it will be minus of VP of the input, whatever input you are having. For example, if this value is 10, it will be minus 10 volt. This is the peak inverse voltage for the simple half wave rectified circuit. So far we have studied this like rectification within just AC source here. Okay, but in practical applications like we have seen in the cell phone charger circuit, okay, we are getting our input from the AC power supply. Okay, so here we are actually using the rectified circuit. So AC power supply is coming, for example, 220 volt AC, okay, for the 3-phase system. Okay, then we actually have to down convert this, okay, to like the 9 volt system, 9 volt AC value, 10 volt AC value. For that we use the transformers. Okay, so we can get the rectified circuit, okay, with a coupled transformer input voltage. Like we have the input voltage, the AC from the power circuit, then we use the transformer here. Okay, so the transformer actually can perform the step up or the step down operation of the voltage. Okay, so the coupling of the this is our rectified circuit. Okay, rectification, half wave rectified circuit, half wave rectified circuit. So we have a coupling transformer here. So the transformer usually performs the step down operation for this application, but it can also perform the step up operation, okay, based on the number of turns of the primary and secondary coil. So this is called primary coil, this is called secondary coil of transformer. Okay, so based on that the number of primary and secondary, we can calculate that what will be the output. So this is called the voltage drop here, this is called primary voltage, this is called secondary voltage. So the ratio of the primary voltage, okay, sorry, the ratio of the secondary voltage over primary voltage, or the ratio of the number of turns of the secondary over number of turns of the primary, it is called as the turn ratio of transformer, and it defines that what will be the value of the secondary output. Okay, what will be the value of the output here. Okay, for example, let's say so we can write V secondary is actually V n times of V primary. Okay, let's say the turn ratio is 0.5. Okay, then let's say we have 10 volt here at the primary side from the AC source. Then the secondary side voltage, it will be 0.5 times 10 volt. Okay, 10 volt at the primary side. Okay, or 0.5 times 10, it will be 5 volt. So here we are getting the 5 volt. So it's step down the input voltage. Okay, so if the value of the n is less than 1, okay, so in that case secondary will be less than primary. Okay, so it's step down. And if the value of the n is greater than 1, so secondary will be greater than primary. So it is step up transformer. Okay, so it can perform both operations, step up and step down transformer.
So another advantage of the transformer is that it will isolate our secondary circuit from the primary the supply. Okay, like in case of a shock hazard or any problem, okay, our secondary circuit will always be protected, because there will be a transfer of the voltage when the transformer is actually working. If the transformer is not working, there will be no transfer, and our secondary circuit, the rectifying circuit, will be completely protected. So this is an example. Determine the peak value of the output voltage across the load and also draw its waveform. So we will solve this example during the live session. Try to solve this at home. Okay, we will try to solve this during the live session. Thank you very much for your time here. See you in the live session.